video cast is about reaction rate. In this video cast, we're going to learn how to write rate law expressions and also see how changing different factors will affect reaction rate. We're going to start off talking about rate influencing factors. So I have a list of my top 5 rate influencing factors. These will increase the rate, and I think you can probably think of quite a few of them on your own. Of course, we want to think about those according to the collision theory. So my top 5 are nature of the reactants. So this just means your what reactants you have, whether they're very reactive or not, or very complex or not, as to whether they will react. So you would want to change those in order to increase the reaction rate. Another one would be surface area. If you increase the surface area by smashing it into small pieces, you have more reactant that is available to react. So it would therefore increase the number of collisions, which would therefore increase the number of effective collisions. Temperature. If you increase temperature, you're going to increase the reaction rate, because as you increase temperature, your particles are going to be moving faster. You raise the average kinetic energy. So they're going to be more likely to hit, and they're going to be more, when they hit, they're going to be more likely to have enough energy, which is part of that component to having an effective collision. The next one is concentration, and here we're talking about molarity, moles per liter. If we're talking about solutions, if we're talking about gases, it would be pressure. With concentration, if you increase the concentration, you're going to increase the amount of stuff that is available. The more stuff you have, the more likely they are to hit each other or collide, therefore increasing your odds of having more effective collisions. I give the little analogy of if in my classroom I move all the desks and I take 2 students and blindfold them and make them run around in my room, I might have a collision. But if I take the entire class and blindfold them and have them run around in my room, I'm going to get quite a few more collisions. And then the last one is a catalyst. Catalyst increases the rate of a reaction, and we'll talk about how they do that here in just a second. So you add a catalyst, it increases the rate of reaction. To slow down a reaction, you would actually add an inhibitor, and they slow down reactions because we don't always want them to be sped up. All right, so let's talk about what a catalyst does. A catalyst speeds up a reaction by lowering the activation energy. So it gives it another pathway. It actually introduces a reaction mechanism that gives it another path that requires less energy. And so it takes less energy to break those old bonds, and then the catalyst comes out of the reaction without actually changing the products. So they just speed up a reaction without actually entering it. And then we can take that catalyst back out and reuse it to speed up other reactions. Now, this isn't necessarily my favorite graph. It's actually 4 energy diagrams that are laid on top of one another. I'm going to talk about them one at a time. So we have our reactants here, and we have our products here. And as this reaction happens, the first one's going to be uncatalyzed. So we have our reactants, and they're starting to collide. They're having to collect a whole lot of energy. And oh my goodness, this reaction is going to take forever because it's having to collect so much energy in order to react and break those old bonds, and we're still not there, and this reaction could take forever. And then, whoo, old bonds are broken and new bonds form. All right, so this reaction would be very, very slow because it has to collect 75, let's say it is kilojoules per mole in order for this reaction to happen. Next, we're going to, in the next graph, we're going to look at what if we have the same substance, except we're going to add a catalyst to it. This time it's going to be a chemical catalyst. So we have different types of catalysts. So again, we start with our same reactants. We put in our catalyst, and in this time, we have to collect a bit of energy, and this is still going to take a little bit, but it's going to take less time because the hill is smaller. Old bonds are now broken, and then new bonds form. All right, so we went from an activation energy of 75 to now an activation energy of 58. So this reaction would happen faster because it has to collect less energy in order to break those old bonds. The next one we're going to talk about is an enzyme. You need to know, we talked about a lot of those in biology. It is important in chemistry as well. And in chemistry, we use enzymes as catalysts to speed up those reactions. We love enzymes because they do one thing and one thing only, and then they don't mess with anything else. So again, we have our reactants, and then we are going to start to collect energy, but this reaction is going to happen very fast. The old bonds are already broken, and then boom, new bonds are formed. We went from an original activation energy of 75 to now an activation energy of 4. So that enzyme did work really, really well in speeding up this reaction and lowering that activation energy. It makes the hill smaller. This last one is what the energy diagram for a reaction that has a reaction mechanism or a series of steps would look like. So we have our reactants, and then some old bonds are broken, and then whoop, intermediates are formed. Then those intermediates may react with some leftover reactant, and then whoop, some more intermediates are formed. These intermediates might react with other intermediates or more excess reactant, and then whoop, our products are formed. So you count the hills. And so this would be a reaction that has 3 steps in its mechanism. All right, the important thing is cows speed up a reaction by lowering the activation energy, and enzymes do function as catalysts. And they speed up reactions. All right, now, rate laws for reactions. We're going to talk about how to write these rate law expressions. So make sure you know what this is called. It's called a rate law expression. And they relate concentration or molarity to reaction rate. We're going to let capital R equal reaction rate and K equal a constant. It is constant for that reaction at that temperature. Now, if I have this equation, we have A plus B yields 2C. To write the rate law for this expression, and they always work the same, it's always R equals K, and then you're going to have square brackets. Remember, square brackets mean concentration in molarity, so you can't substitute parentheses in here. So square brackets, and it's going to be A times, okay, so again, even though there's a plus sign in the reaction, here we've got times in our rate law, times the other reactant, which is B. Notice you do not see your products in here. We do not see C in this one because it is a product. And really, if you step back and think about it, for a reaction to happen, it really only matters the concentration of the reactants, because those are the things that need to be colliding and reacting. All right, so that will tell us a little bit. So we know that it's always R equals K, and then we multiply the concentration of the reactants. There's one more little piece, so we're going to use another example, this one, to write the rate law expression for that. So, the rate law expression for this, following the same sort of pattern, it's R equals K, and then square brackets, concentration of our only reactant, which is C. But what do we do with this coefficient? Well, it is raised to the coefficient power. So if the coefficient over here had been a 3, then we would have a 3 over here. But the way it stands, there's a 2, and so it's just squared. All right, so rate law expressions always start R equals K. Then it is the concentration of the reactants multiplied together raised to their coefficient power. Remember, if we're looking at substances like chlorine gas, that is not a coefficient. That is part of its identity. So we would not raise that to the second power. That would just be Cl2 in square brackets. Now, if there were a coefficient in front of it, that we would raise it to that power. Okay. Let's practice with this one. If I have 2NO plus F2 yields 2NOF2. Let's just make it this. Okay, so if I wanted to write the rate law expression for this one using actual chemicals instead of A's and B's, it would be R equals K times the concentration of my reactants multiplied together, raised to their coefficient power. The coefficient for NO is 2, so I would have to square that one, and it does go on the outside there. All right, so that's how you write a rate law expression. Now, what if we have a reaction mechanism? How do we write the rate law expression for that? Well, if a reaction has several steps, we must find the rate determining step, which is going to be your slowest step. How do you know which one's slow? Because they're going to tell you. You would receive all of this information in a problem like this. So you have to know that you're going to use the rate determining step, which is the slowest step. So that would be step number 2, and we base our rate law only off of that slow step. So if we're writing our rate law expression for this one, it's R equals K times the concentration of NO3. That is a 3 here. I don't know why it wanted to cut off those. And then times CO. And that would be my rate law expression for this entire reaction, because the fast one just happens, and it doesn't really affect our rate like the slow one does. Another thing I can ask with this is, what if, or give me the overall reaction. If we want to do the overall reaction, then we're just going to add these guys together and cancel out what we can. So our intermediates here, intermediates are formed and then consumed. So that would be NO3. NO3 is formed in step 1 and then used up in step 2. So that's an intermediate. There's one more thing that gets canceled out here, and that would be NO2. NO2 is there at the beginning and it's there at the end. It is not an intermediate. It would be a catalyst. Catalysts are there in the beginning and they're there at the end, and then we can take it back out and reuse it. Now we're just going to write down everything that's not crossed off. And that's your overall equation for that one. Notice the rate law is not based on the overall equation. It's only based on that slow step. All right. So, practice with this one. Write the rate law expression for this reaction. Okay, so you should have gotten this. Now, once we have that rate law, another popular type of question that's going to come after that is, what happens to the rate if? All right, and then you have different scenarios. Some of you will have no problem figuring out these. Remember that capital R equals your rate. Others of you, it takes a little bit of mental processing. So I'm going to show you a strategy that you can use to help with that. One thing, we're changing something, but they didn't give us what we're changing from at all. So you have no starting point, and that can make it difficult. So the way I do that is I say, if they don't give you a starting point, you get to make one up. And if you get to make one up, you get to make it easy. And I am going to do just that. So I like to make my little starting point. And I'm going to say, well, I don't know what K is. It's a constant, and so I'm going to say it's 1. They don't tell me the initial concentration of X, so I'm going to say it's 1. And they don't tell me the initial concentration of Y, so I'm going to say it's 1. Now, it would still be squared because that's the formula for my rate law. If all that is true, then what is my rate? 1. Okay, now we're going to compare everything to this. So now we can make those changes. So the first one says, what if we double the concentration of X? So you're going to plug it into this formula. Everything's going to be the same, except we're just going to double what X is. So K is still 1. X is now 2. We've doubled it from our starting point. And Y is still 1, and it's still squared because that's the formula. If that is true and I multiply this out, my rate is 2. So from here to here, my rate did what? It doubled. So rate doubles. Or you could say increases by a factor of 2. Well, next one. What if we just double the concentration of Y? So we're going to go back to the start, and we're going to see what happens if we double the concentration of only Y. So we plug everything in. K is still 1, X is 1 because we went back to that starting point, and we're just going to double Y, which is now 2. And it's squared because that's what the formula says. If that's true, what is my rate? 4. So my rate went from 1 to 4, so it quadrupled. So rate quadrupled, or increased by a factor of 4. Next one. What if we decrease the concentration of Y to 1/3 of its original size? Okay, so I'm going to go back to the start. K is 1, X is 1, Y is 1/3 of its original value. So it's 1/3, but it's still squared. Now, if all this is true, then what is my reaction rate? 1/9. We compare these two numbers here, and our rate decreases by a factor of 9. Don't just tell me 9. Okay, it's going to decrease by a factor of 9. And that's how you solve those sorts of problems. And we'll talk about this a little bit more.